we were talking about orthogonal transformations and isometries. Okay, I remind you that isometries are things or transformations that preserve the length. All right, and we got this result that isometries would be expressed if we can, if we are in finite dimensional spaces, would be expressed by an orthogonal matrix. Okay, and I remind you then an orthogonal matrix is going to be some matrix such that M transpose times M is equal to the identity, or M times M transpose is equal to the identity in another. In other words, that the inverse is given by the transpose matrix. Okay, so let's do some kind of systematic exploration of all the isometries we get in R2 and R3. Last time, we saw some of them. We saw the orthogonal symmetries. These, and we showed that linear orthogonal symmetries in R2 and R3, we explored them, we found out how they would be expressed, how we could find their characteristics. Okay, that's what we did during the tutorial. And okay, that's what we saw. But this is only a small, well, one part of the possible linear isometries that we can find in R2 and R3. So let's go on this exploration and let's see what we have in R2, okay, in the plane, planar isometries. So let's say, so we're going to get some, actually some very exact matrix for those. We will show that we've got an isometry if we can find some angle theta such that the matrix is expressed this way. And furthermore, so you see you have those choices of signs. If we have a minus sign here, we will get a plus cosine. And if we have a plus sign here, we will get a minus cosine. And so if we make the specific first choice, well, if it corresponds to that specific minus here and plus here, so this one, okay, it corresponds actually to a direct one. Okay, so I remind you, O2, the set of orthogonal matrices in dimension 2, and special ones, SO2, are the ones that are going to be called direct, and they will correspond to a determinant is equal to 1, and here the determinant is equal to plus or minus 1. Okay, that's not enough to make an orthogonal matrix or an isometric, but that's one of the properties we have. Okay, all right, so let's show why this is true. Let's start. If we have a matrix M that is in R2, it just means that it has those 4 values, A, B, C, D, and we're going to find conditions on A, B, C, and D such that this matrix is orthogonal, right? So let's try that M transpose times M is equal to the identity. What does it mean? So M transpose is going to be, I'm taking the first row and I'm making it the first column, so that's AB, and then second row becomes the second column, CD. Another way to see that is that you exchange the rules of coefficients on each side of the diagonal. B takes the rule of C and C takes the rule of B. Okay, so but it's pretty easy in dimension 2, I guess. Okay, so that was MT times M, so that's A, B, C, and D. And if I write this matrix multiplication, I get A squared plus C squared. I get AB plus CD. I get BA plus DC, so again, AB plus CD. And I get B squared plus D squared. And if this is an orthogonal transformation, I should get that this is equal to 1, 0, 0, 1. So let's see what it implies. It means that A squared plus C squared is equal to 1 on one hand. But also I've got that B squared plus D squared is equal to 1. So how can we interpret this? The sum of squares is equal to 1. That should remind you well of Pythagorean theorem. Okay, so it means that I can interpret that by saying that there exists some theta, some angle theta, such that A would be the cosine of theta and C the sine of theta. Okay, that's one way to interpret this. Okay, and similarly for the second one, except it doesn't have to be this. Well, there's no reason that it is the same angle. So there exists some other angle phi such that b is equal to the cosine of phi, and c is equal, and d, sorry, is equal to the sinus of phi. All right, let's see what we have furthermore. We also have that AB plus CD is equal to 0. So using the above notations with the cosine of theta and the same stuff for the phi, we get that should be cosine of theta, cosine of phi, plus sine of theta, sine of phi is equal to 0. But here you can identify an addition formula, a trigonometric addition formula. That would be the cosine of theta minus phi, or phi minus theta. It doesn't matter. It's just it's even. All right. So I get that this cosine is equal to 0. That means that theta minus phi is equal to plus or minus pi over 2. Modulo 2 pi, but let's take one main measure, which would be plus or minus pi over 2. So I've got those two possibilities. All right. One more thing that we can remember is that if I say that, for instance, the phi is equal to theta plus or minus pi over 2, we can also write it this way. We should remind us that, well, the cosine is this one, and then we have that the sine is, well, the same one but shifted by pi over 2. So what do we get? We get those shifting formulas that tell us that the cosine of theta minus pi over 2 is given by the sinus of theta. That's going to be the shift of pi over 2, and the sinus of theta minus pi over 2 is giving you minus the cosine of theta. And if I make a plus, if I take the cosine of theta plus pi over 2, I'm adding pi, so it gives me the opposite actually, so that's going to be minus sinus of theta, and similarly the sinus of theta minus pi over 2 is going to be the cosine of theta. So the two choices that you see here, that corresponds to one or the other choice, right? So maybe we can rewrite this more clearly. So we have, if we take that phi is theta minus pi over 2, so let's take this first choice. That's giving us, so A is going to be, so we said, what did we say? What did we say? What did we say? Sorry about that. We said that A would be the cosine of theta, and we said that B would be the cosine of phi, but then phi is theta minus pi over 2, so that would be sinus of theta, okay? And then C would be the sinus of theta, and D would be the sinus of, if I'm not mistaken, sinus of phi. In the case of theta minus pi over 2, that's minus cosine theta. Okay, and that's one possibility. And if I do the other choice, we will get is equal, well, to the other one. So cosine theta, I get a minus sine theta, I get a sinus theta, and here a plus cosine of theta. And the difference between those two matrices is that in the first case we get that the determinant of m is minus cosine square minus sine square, so -1, and in the second case the determinant of m is cos square plus sine square is +1. Okay, so and you can remember that if we take the specific cases of the of the orthogonal symmetry that we treated last time, that corresponds to some specific choices of theta. That would correspond to well, if you take theta is equal to 0, for instance, or theta is equal to pi, that would be in the first one a linear isometry. Okay, that gives you the central symmetry. No, that doesn't give, that gives you well, the one we studied with respect to some specific one. All right, and then if I choose theta is equal to 0 or pi, again in that case, that would give me either the identity or negative the identity, which are also some cases of isometries that we studied last time. Okay, so let's see some general identification method, what it corresponds to. Okay, so first of all, given some matrix, two matrix that you suspect is a linear isometry, so you multiply A by A transpose, or A transpose times A, and you get that it's equal to the identity. Then you know it is going to be it's an orthogonal matrix, and so it represents an isometry. You calculate the determinant of A. If it's +1, you've got a direct one, and the simple cases are when you've got the identity, okay, or minus the identity, okay. So, and that makes you the central symmetry that we saw last time. Otherwise, it's a rotation, okay. In the case of determinant A is equal to 1, and we need to identify the rotation, why we have a rotation and the angle of this rotation. Okay, so let's study that direct isometry case. So we said direct isometry in if we are not in the simple case. So I remind you that in that case, direct isometry, we have this matrix. We have cosine theta minus, it corresponds to this one, minus sine theta, cos theta, and sinus of theta. Let's look for the eigenvalues, right? So we write the characteristic equation. It's cosine theta minus lambda square plus sinus square of theta. Okay, so we expand that. We're going to get lambda 2 minus 2 cosine theta times lambda plus cos square minus sine square plus cos square, sorry, there's a plus here, plus sine square, that makes a +1. Okay, so if I'm looking for the roots of that stuff, I'm going to get so the delta is minus well, 4 times cosine square minus 1, still minus, well, minus 4 times 1, so minus 1. Okay, and cosine square of theta minus 1, that's minus sine square, so minus 4 sinus square of theta. So unless the sinus is equal to 0, okay, in which case we have theta is equal to 0 or pi, which corresponds to the cases we've already talked about, the identity or minus with the identity, we get two roots, lambda 1 and lambda 2, that are going to be complex roots. So we get, in the first case, cosine theta, minus 2 cosine theta plus or minus I times 2 sine theta divided by 2, and minus 2 cos theta minus I2 sine theta.